Welcome to this class. So, we continue fractional factorial design. In last lecture, I have given you the concepts, what is fractional factorial design and why it is needed, how does it work, what is generator for fractional factorial design. And in this process, I told you that what is confounding and what is alias. In this lecture, we will continue with all those things, and the content is we will start with the anatomy of fractional factorial design, then aliasing and de-aliasing with example, and finally design resolution. So, last lecture you have seen this slide. What I have said that if you go for 2 to the power 3 factorial design, there what happen, you require 8 runs, 2 to the power 3 design 8 runs. So, we have shown you that with generator I equal to ABC or I equal to minus ABC, you can reduce the number of runs to 4, and in that process you definitely lose some information, but because of the properties like sparsity of effects principle, projection property and sequential experimentation, you are still in a position to analyze and get useful results. So, the 2 to the power 3 design with factors A, B, C, let us see the geometric view. You say the first half I equal to plus ABC, you are conducting experiment at this factorial point, this factorial point, this factorial point and this factorial point. And if you do this, you will be using this factorial, this 4 factorial points. Now, you have to find out the effect of A, effect of B and effect of C, the main effects. Instead of writing that A equal to this, here we are writing LA, LB and LC. It has a specific purpose of writing LA and LB and LC, which will be known to you little later. Now, we all know that what is the effect? Effect is the contrast by 2 to the power k minus 1, here n is 1. So, 2 to the power k minus 1. Okay. So, here what is happening, you are actually doing, because of fraction you are doing 2 to the power 3 minus 1 means 2 to the power 2 design. So, in 2 to the power 2 minus 1 again, that means 1 by 2. Now, A minus B minus C plus ABC, these are the, this is basically the contrast for A as well as BC. Let me see. Okay. What will be the contrast for A? This into this, that is A, this into this, this is minus A, this into this is minus C, this into this is ABC. So, here your contrast for CA is then A minus B minus C plus ABC. I told you that A is confounded with BC. If you see the contrast for BC, you see that also A, and this is basically equal to contrast for BC. So, we know the effect is 1 by 2 to the power k minus 1 into n contrast, that you know earlier. So, now n equal to 1, k minus 1, here k equal minus 1 design. So, it will be this again minus 1. So, that means 1 by 2 into here, if I say this is the effect of A, then A minus B minus C plus ABC, but this also effect of BC, include effect of BC. So, as a result, we are writing only one we are using the word L and writing LA. because A's effect and BC's effect are confounded. So, this means we can say A plus BC, that is the purpose. So, once you have this kind of design, you know the contrast, you know the effect, and in the slide itself, you see LA equal to this, LB, LC. Now, from the table you can find out all the contrast and get the main effects and interaction effects. Okay. So, calculation is possible, but as I told you, this calculation is aliased. This is alias structure, because LA is not effect of A only, it is basically effect of A and BC, that is why A plus BC. LB is B plus AC, LC is C plus AB, so like this. Okay. So, if you see that for the that LA equal to again LA will be equal to LBC, LB equal to LAC and LC equal to LAB because of the contrast structure, you see. So, truly speaking, there is confounding, and then they are known as alias structure, A with BC, B with AC and C with AB. Okay. Now, how do get the alias structure? How do you get? You see here your generator I equal to A BC. If you multiply it with A here, you are getting BC here, because this is A square BC equal to BC. So, that is why we are saying A and BC are aliased, A and BC. Similarly, B and AC, C and AB. Okay. And if you will find out, okay, so this is what is the alias structure in this design. Now, what you do, instead of using this, you use I equal to minus ABC. If you use I equal to minus ABC, then let me go back to this. So, that means this side, the lower portion half you are using. Here, what is the contrast for A? A contrast for A is your AB plus AC minus BC minus 1. Then, what is the contrast for BC? CBC, if you see, the contrast for BC is minus AB minus AC plus BC plus 1. What is happening then? That means this is minus CA. Okay. So, as a result, if you use this half, the second half, then when you compute LA, which is 1 by 2 AB plus AC minus BC minus 1, this is nothing but also minus this is basically minus of this, minus of CA is there. So, BC, CBC. Okay. So, as a result, what happened, this LA, when you compute like this ultimately relates to LA relates to A minus BC. So, using this half, you are getting LA equal to A plus BC. Using this half, you are getting L equal to DC. So, we will use a dash here, that is all. Now, if I use L dash A, then it will be A minus BC. So, if you do two fractional design, then in the first design using I equal to ABC and second design I equal to minus ABC, then the first design you get this estimate and the second design you get this estimate, then you are in a position to uniquely estimate A and B, because half of LA plus L dash A will give you A here, and half of LA minus L dash A will give BC here. So, that is the advantage, as I told you, that if you go for sequential design, first half may be using this, second may be using this, and then what will happen, combining the two you will be getting the unique estimates. Okay. So, if you see this table using half L I plus L I dash I from ABC and L I minus L I dash, you will be able to find out the main effects and the second order interaction effects. Okay. So, this concept is known as D-aliasing. This concept is known as D-aliasing, and either this one, when you use one half and we get like this or like this is the aliasing one. So, in order to de-alias, you require to have the other fraction also when it is half fraction. When it is 1/4 fraction, you require more. Okay. Let us see one example here. After doing so much of fractional things, let us see one example. This is an example where there are 4 factors A, B, C and D, and you require 2 to the power 4 means 16 experimental runs with single replicate, but you do not want to do this because you have problem, resource problem. So, what you want to the power, you want one half fraction to the power 4 minus 1, that means to the power 3 means 8 runs. So, how do you do this? It is given here. So, the procedure is, if 2 to the power, although I have A, B, C, D 4 factors and I require 2 to the power 16 runs for complete factorial design here, but you are going for 2 to the power 4 minus 1 means 2 to the power 3, that means 8 runs. So, that means at least in 3 factors A, B and C, let this is full 2 to the power k factorial. So, then what will happen to D? What will happen to D? So, it is said that D should be related, or D should be confounded to the highest order interactions of ABC, then it will be ABC. Need not be, it should be confounded with ABC third order interaction, it may be with AB also, but it is suggested that the confounding should be with the highest order interaction for better result. So, if that means your design will become like this, you see here. So, for A, B, C, you see that the full 2 to the power k factorial written here, minus plus minus plus up to 8 minus 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 plus this. Then you find out the highest order interaction A, B, C. So, you multiply all the, you are getting this. You are saying that D will be set like this. If you choose D like this, then what is happening here? Your treatment combinations are this. First one is the all low, second one A, D high and something like this, and with this treatment combination you have done the experiment and you get the filtration rate, that is the response values. Now, you may say that what will be the value of A, B, A, C, B, C, you can multiply. Now, you will be getting everything. So, if you use D equal to ABC here, then if I multiplied this with D, then it will be D square, then it will be ABCD, and D square means it is I equal to ABCD. Okay. So, I equal to ABCD, this is what is the relation. So, then if you, now it is possible, suppose you what you do, you multiplied all the columns here, 1 minus minus, you will find out that If you multiplied A, B, C and D, you will get I means all positives. Okay. Let me tell you one more thing. Suppose if you do not, if you say D equal to AB here, what will happen? Then what will be I equal to ABD. Please keep in mind the number of words in this relation. This is very important. Here if D is confounded with ABC by design, then I equal to ABCD, this is 4 word, you are getting 4 word relation. If you instead of confounding with AB, if you do with ABC, if you confound D with AB, then the defining relation here we have 3 word. This word business is also equally important. So, I equal to this, how many words? Here I 3 words and here 4 words. Okay. So, now let us do some calculation and then again we will come back to the concepts. So, with this data, so you want to estimate A. So, instead of A, you will estimate A within bracket, because this is nothing but A plus BCD. Why? Because this alias structure you have to find out. You can find out this I equal to ABCD. If you multiply this with A, you will be getting BCD. If you multiply this with B, you will be getting ACD. With C, you will be getting ABD. With D, you will be getting ABC. Suppose you multiplied with AB, what will happen? AB, if you multiplied with AB, you will be getting CD. If you multiply with AC, you will be getting AC multiplied BD. If you multiplied this AB, AC, AD, you will be getting BC. If you multiplied this with BC, you will be getting AD. If you multiply this AB over, AC over, AD over, BC already done, BD done, CD done. Okay. Now, if you multiply this with ABC, you will be getting D. So, that means multiplying the one or other factors, you will be getting another factor in this kind of, this is the aliasing structure. So, fine. So, suppose I want to, from using this data, when you compute A, you are basically computing A plus BCD. So, this is what A 19, AB minus 1, that AB also you can compute. In this manner you can compute other effects also, all the effects with the alias structure. Here 2 important things to be noted here. One is that the effect value, whether it is large or small. If effect value is large, then the effect with its alias is significant. If the effect value is small, then the particular effect with alias that may not, that is not significant. In the first case, it is significant. Now, which one is significant? Are both of them significant, or one of them significant and another one is not significant? How do you find out? In the second case, are both of them insignificant, because the total is insignificant, or individually they are significant and collectively they are insignificant because one going in opposite to the other directions. So, it is a little interpretation issue, little complex from that point of view also. But we have some rescue. One of them is Occam razors. Occam's razor is basically coined by William Occam. who said that a scientific principle, actually the scientific principle that when one is confronted with several different possible interpretation of a phenomena, the simplest interpretation is usually the correct one. Okay. What does it signify? Signifies, suppose here we are saying A and BCD together the effect is 19. Now, again the paucity principle says that the higher order interactions will be, effect will be negligible compared to the lower order interaction. So, it is quite obvious that A effect is significant as A plus BCD effect is significantly large, 19. So, A is significant because from paucity of effect principle BCD effect will be much lower than A. In some case, in any case, if we can found that BCD effect is negligible, then we can take this 19 as effect value for A. Okay. Another viewpoint is the standpoint of effect heredity. What is this? Suppose that AB is significant and that both main effects A and B are significant. In that case, it is a strong heredity. The reason is A and B are significant and AB also significant. So, another one is that suppose AB is significant, but one of the A and B are not significant. So, then it will be weak heredity. Okay. So, this also, this is basically less common, that is basically this is less common. So, that's why these two principles helps us to focus on the effect when it is estimated using this Alias structure. Okay. So, with this explanation, now see the effects and their Alias structures. A 19, B 1.5, C 14, D 16, AB minus 1, AC this like this. So, here A, C, D, AC and AD they are large. So, significant compared to B and AB it is really significantly large. So, as B value is low, so we can assume that it is not significant, and here AB is value is also very low. Okay. So, this is also not significant. Now, as AB is aliased with CD, so AB plus CD, you may say that this value is low, maybe AB is in the positive side and CD affecting negatively. So, that is why this is low, but this occurs hardly occurs, this kind of things occurs hardly. So, all practical purposes it can be assumed that A, C, D, AC and AD are significant. Okay. And using this AC all those things, this regression equation can be developed. Now, once you develop this regression equation, now your another work you can do, you can develop response surface, you can go for contour plot, you can set the parameters at different levels and to get the, you can optimize this also. So, things are possible. Okay. So, this is what is in case of fractional factorial design, how do you design for fractional factorials. Then once you conduct the experiment, the experimental data, how do you analyze? Using contrast only you analyze the effects, and then from there, as there are Alias structures, so you cannot separate out some of the effects from the other effects. So, using the Occam-Razors and heredity principles as well as the sparsity of effect principles, so you are in a position to conceptually eliminate some of the low value effects. Okay. And this you have seen earlier the probability plots also, the normal probability plots and effects to find out the which are the effects they are significantly larger than others. The last concept in this lecture is the design resolution. Okay. So, you have seen example that 4 factor ABCD. In this particular case, you see that the example, where is the example? This example, you have seen that we have considered 4 factors and I equal to ABCD is the defining relation. Okay. So, the generating relation or defining relation I equal to ABCD, it contains 4 letters. Usually, this talks about the resolution. The higher the resolution, it is better the design. If I equal to contain 4 words, then it is design resolution is 4. So, that is why this in this example it will be said at 4 minus 1 4. That means what is then that 2 to the power 2 to the power 4 minus 1 resolution 4. This will be written like this: fractional factorial design 2 to the power 4 minus 1 comma resolution 4. Okay, resolution 4. This is the design. Now, as I told you that here why this resolution is, you got the higher that 4th resolution, because you have confounded D with ABC when you have started the design, and accordingly you got I equal to ABCD. If instead of this, if you say D equal to AB, then I told you I will be ABD. Now, how many words? It has 3 words. So, here if you do this, and accordingly the algebraic sign table will change, the contrast will change, alias structure will change, everything will change. Then what will happen, that this design will be known as 2 to the power 4 minus 1 3. So, this fractional factorial design 2 to the power 4 minus 1 resolution 3. Okay. Obviously, this is better than this. The reason is here you see D is confounded with higher order interaction in comparison to this. Here third order interaction, here second order interaction. Paucity of effect principle says that if this is significant, this will also be significant because AB lower order. So, that this design is not good compared to this in general. So, it is recommended that you go for higher order designs. Okay. Now, suppose I will ask you question like this, that given that I equal to ABD, what is the alias structure? If you multiply this with A, what you get? You will get B. But if I equal to ABC, if you multiplied with A, what you are getting? ABCD, if you are getting BCD. See, the alias structure is also changing. So, depending on what kind of resolution you are considering, that will ultimately change the alias structure. And obviously, if you have enough expertise on the process, the physics of the process, and where you think that it is better to confound D with AB instead of ABC, then obviously you go for this other design. That is what is what basically the common sense explanation. Some of the guidelines: if you go for resolution 3 designs, no main effects are aliased with other main effect. Main effects are aliased with 2 factor interaction, and some 2 factor interactions may be aliased with each other. Example is this: in resolution 4 design, no main effect is aliased with any other main or 2 way interaction effects. two factor interactions effects are aliased with each other. Example is this. If you go for higher order like resolution 5 design, no main effect or two factor interaction effect is aliased with any other effect, main or two factor interaction effects. No two factor interaction effects are aliased with any three factor interaction effects. Example this. So, from here you can understand the alias, how the alias structure is changing if you go for higher order resolution, and it is obvious that the more the resolution, the better is the design. So, I already explained most of the thing like higher order interaction negligible, redundancy, that means a fractional factorial design employ redundancy in arranging that lower order effects are confounded with those of the higher orders, that are negligible. Parsimony, the active factor space is frequently of lower dimension than the design space, means actually if you have many factors, the design space is a bigger one, but actual active that space basically that will be lower than the bigger one. And then projectivity is important one. As I told you that any fractional factorial design of higher order is basically full that factorial design at the lower order. So, that is known as the projectivity. So, if you project a higher dimensional issue into lower dimensional issue, you will have full information at the lower dimensional issue. And there is interestingly, suppose if it is 2 to the power 3 minus 1 design, then projectivity is 2, because in 2 dimension it is full factorial, all factorial points are captured. And now that is why what happened, and it is there is a relation between the resolution and the projectivity, that projectivity is resolution minus 1, keep it in mind. If projectivity is P, resolution is R, then R equal to or P equal to R minus 1, P equal to R minus 1. So, if your defining relation is ABCD, then your resolution is 4, R is 4. If it is ABD, R is 3. See here in 3 projectivity will be 3, that means in 3 dimension full information you are getting, but here you are getting full information in some of the cases only in 2 dimensions. So, resolution has very good effect in case of lower order analysis also. Okay. So, this is the way, that mean the projectivity part we have explained. I have explained this one. You see that third or 2 to the power 3 design, and if you do even fractional factorial 1/2 of it, you will in the at least in the AB level or here AC or BC level you will be having full information, provided it is the resolution is 3. The lecture taken from Montgomery's book Design and Analysis of Experiment. So, thank you very much, and I request all of you to carefully read the chapter of Montgomery for fractional factorial design. The concepts and other thing what we have discussed here, they are not simple, they looks to be simple, but they require a careful reading, and I hope that you will be able to do the assignments, and also will be able to score high. That is all. Thank you very much.